Thanks for coming, and thanks organizers for inviting me to this great workshop. I'm going to talk about learning mixtures of Gaussians again, but this time we'll learn a mixture of general Gaussians. This is based on joint work with Xingxing Huang and Sham Kakale. So although Sham already introduced the learning mixture of Gaussians problem, there's a nice story there that I want to tell. So there's a story about crabs. So in late 19th century, zoologist Weldon, he caught a lot of crabs, and for each of the crab, he measured this forehead over body length ratio for a lot of crabs. And then it turns out this ratio is distributed like this distribution. So Weldon saw this distribution, and he felt this is not normal. Normally, it should look like a Gaussian distribution. So this, of course, is nothing like a Gaussian distribution. So he went to Pearson for help. And the idea they had is, well, maybe this means that this, whatever, 1,000 crabs he caught, it's not just one kind of crab. It might be two different species of crabs. Each kind of crab will have, if you can distinguish them, each kind of crab, if you measure this ratio, it will be distributed like a Gaussian distribution. But because these two kinds of crabs are mixed together, when you plot the density function of this ratio, it becomes a mixture of two Gaussian distributions. So the density function will just be the sum of two Gaussian, sum of the density functions of two Gaussian distributions. So now the problem becomes, I already know this density function. So does this give me enough information for me to tell what should be the parameters for the two Gaussian distributions if I can separate them? So what are the means, variances, and mixing weights for these two Gaussian distributions that when you take the sum of their density function, they look like that? And Pearson had a very nice algorithm for solving this. It's based on the method of moments. So you compute the first 6 moments. Moments are just expectations of polynomials. First moment is just the mean. Second moment is the variance, and so on. So after you compute all these 6 moments, it gives you a lot of equations on the parameters, on the unknown parameters, the means, variances, and so on. And then somehow he can solve this set of equations and get the correct parameters. So indeed, this distribution is the sum of these two Gaussian distributions. And this kind of algorithm is later known as the method of moments, and it has become really popular in statistics. So more concretely, learning mixture of a Gaussian problem, you are given samples from one out of k Gaussians. In the previous case, it was in one-dimensional, but it doesn't have to be. It could be in some high-dimensional space, say n-dimensional. The goal is to find the mean and the variance and the mixing weights for all these different Gaussian distributions just by observing the samples. Here's another example that's in 2 dimensions. You get these points, and maybe they come from the mixture of these two Gaussian distributions. So essentially, Pearson's algorithm, or Pearson's argument, shows that we can solve this problem when the dimension is 1 and the number of Gaussians is 2. And we can do this just by estimating the first 6 moments and solve a set of polynomial equations. Later, this result is generalized by Moitra and Valiant. They show that the same idea can actually be used to to learn a mixture of Gaussians for arbitrary number of Gaussians and arbitrary number of dimensions. And instead of the first 6 moments, they use the first order k moments, and k is the number of Gaussians we want to learn. So this is very nice, but there's a problem here. So it uses order k moments, but we are not given these moments directly. We are given these samples. So we need to estimate the moments from the samples. And it turns out in order to estimate all these moments accurately enough for the algorithm, we will need number of samples we need will be exponential in the number of Gaussian components. And also their algorithm also runs in time that's exponential in this parameter. So this is not very good if this number of Gaussian component is too large. Say if there are 10 different kinds of crabs that we cannot distinguish, then if we want to distinguish them using this algorithm, maybe we need to catch all of the crabs in the world, and we still don't have enough samples. So the crabs are not so happy about that. But how can we solve this problem? Well, let's look at the crab story again. It's usually told in the way that I just told you, but in fact, Weldon, of course, didn't just randomly came up with the feature that the forehead over body length ratio. It doesn't make sense, right? So instead, he made many more measurements. He measured maybe all these lenses and all the ratios between these lenses. So what this gives you is it will give you a mixture of Gaussian in much higher dimensions. Well, by the way, the reason that they only looked at that particular statistics is because that's the only statistics that looks significantly different from a Gaussian distribution. But of course, even you can still be a mixture of two Gaussians. Maybe they are very close like this. Then you still look like a Gaussian, but in fact, that's not true. And maybe there are useful information in all these other dimensions that they didn't use. So why do we think that having a mixture of Gaussians in higher dimensions should help us? Well, because usually higher dimension things are harder to compute, but in this case, higher dimensions gives us much more information. In particular, if we use the method of moments, because if we use method of moments, if we are in one-dimensional, then first k moments just give you k numbers. But if we are in high-dimensional, say, then the fourth moment, for example, is defined to be the expectation of all these correlations between different coordinates. Each coordinate xi1, xi2, xi3, and xi4. This I1, I2, I3, I4 can be chosen from 1 to n, and recall we are in an n-dimensional space. So this fourth order moment really forms a symmetric fourth order tensor. So when we have, say, 20 dimensions, the fourth moment tensor has more than 4,000 distinct parameters. It's really 23 choose 4. But on the other hand, in 20 dimensions, every Gaussian component will have only 231 parameters. This includes the parameters for the mean, for the covariance matrix, and for one extra parameter for the mixing weight. So naively, all these parameters should give us some polynomial equation over these unknown parameters. So naively, we have more than 4,000 equations. We have 231 times whatever number of Gaussians. That's the number of unknowns. So in the best case, we should be able to hope to learn 20 Gaussians using just the first order moment. And of course, when n grows, if this number will grow as n to the 4, this number will only grow as n squared. So we can even hope to learn even more Gaussians. But of course, this is just a heuristic argument. We cannot really solve system of polynomial equations. Also, these equations might be redundant. But luckily, in some special case, indeed, in the algorithm that Sham just talked about, we can make use of this high-dimensional structure. And indeed, it makes learning mixtures of Gaussians easier. So there are a series of works on learning spherical Gaussians. So the first one is what Sham just talked about, the work with Daniel Xu. So they can learn a mixture of k spherical Gaussians using just second and third moments. And their algorithm works whenever the means are linearly independent. But in order for this condition to be satisfiable, we need the number of dimensions to be larger than the number of components. So later, there are some follow-up works that improve this result. So basically, there's one work that Arvindan is going to talk about this afternoon. What they show is you can learn mixture of k Gaussians using constant number of moments when the dimension is larger than k to some epsilon, where epsilon is also a constant. It can be an arbitrarily small constant, but the number of moments you need will depend on epsilon. And their algorithm works when the means are perturbed, which I will make more precise later. For now, just think when the means are in general position. There are other related works that are really very similar to this work. They give similar guarantees and trade-offs. But unfortunately, all these works still only work for spherical covariance matrix or maybe some other highly structured covariance matrices. If the covariance matrix can be quite general, it does not work. And for example, in the crab case, the spherical covariance matrix really correspond to the assumption that all these different ratios or lengths or whatever statistics we measured, they have to be independent, which is not very reasonable in many settings. So in this talk, we will really try to learn a mixture of k Gaussians in polynomial time, and even if they have general non-spherical covariance matrices. But we cannot hope to do this in the worst case, as Moichel and Valiant showed this is impossible if you just use a polynomial in k number of samples. So instead of the worst case, we hope to work in this smooth analysis setting, which is mentioned in the last talk. So smooth analysis is first proposed by Spielman, Mann, and Tang. It's used to analyze simplex algorithm for linear programming, but it's also very reasonable for many of the learning settings, actually. So in this case, the instances, the algorithm do not get worst case instances. Instead, the instances are perturbed locally before they are given to the algorithm. So it's like, so first an adversary can choose an arbitrary worst case instance, but before giving this instance to the algorithm, some either nature or some good guy will perturb the instance locally at random. And then this perturbed instance is given to the algorithm. So the underlying idea is maybe we are trying to learn these true parameters that arise in nature. These true parameters, maybe we shouldn't think about them as a fixed number because these numbers are themselves noisy. Maybe this whatever ratio of the crab depend on the climate of the year, and if you do it in different years, they are slightly different, right? So the true parameters, you should really think about it as something that's locally perturbed around a fixed value. Algorithmically, if you have this perturbation, it helps a lot by avoiding degenerate cases. If I have a bunch of points in a high-dimensional space and I perturb them, then there will be no 3 points on a line, for example. So in the mixture of Gaussian case, this corresponds to the adversary will first choose a mixture of Gaussians. So basically the parameters, the means, variance, and mixing weights. And then these parameters are perturbed. And then the samples are generated according to the perturbed parameters. The algorithm sees these samples, and the goal of the algorithm is really to learn the perturbed parameters.
But usually, mathematically, if you have a problem, something singular, if you take the perturbation, you must have it also in numerical method that you still have problems.
Well, so smooth analysis setting, I think in some sense tries to say that will not be the case for this particular problem. For example, if you have an arbitrary matrix, of course it can be low rank, right? If you try to do an inverse, it doesn't work. But if you randomly perturb it, it will be full rank. But of course, as you said, there could still be a problem that although it's full rank, it might have really bad condition number, which will make your life hard again, right? But in this case, for example, for matrices, we know if you do a random perturbation, at least for some random perturbations, the smallest singular value of the matrix will be bounded. So the condition number of the matrix will, with high probability, not be so bad. And that is a case when, after you do the perturbation, it makes things reasonable. So here's a picture to illustrate the idea. So for a general problem, even if it's hard, it might have some easy instances. But the distribution of easy and hard instances can be quite arbitrary. It could look like that. But if I have an algorithm that works in the smooth analysis setting, then this really cannot be the case because, for example, if I'm here and I'm perturbed locally, I'm still in the hard region. I cannot solve my problem. So if I have an algorithm that works in the smooth analysis setting, it really means the problem should look like this. Most instances are easy. There are some hard instances. But in any small local neighborhood, most of the instances are still easy. And in this talk, we will work in the smooth analysis framework. We will assume the entries in the mean and the covariance matrices are randomly perturbed by some Gaussian noise. So in this model, our results show that given samples from this smooth mixture of k Gaussians, in the first case, we assume all these Gaussians have zero mean. So their means are zero and not perturbed. So in this case, if the number of dimensions is much larger than 100k squared, k is the number of Gaussian components, then we can learn all these parameters in polynomial time and polynomial number of samples. And all of those are with high probability over the perturbations that we do in the smooth analysis setting. Yes?
You think of rho as a constant here?
You mean the perturbation, the variance of the perturbation? Yes. So rho, we should think about it as a parameter that can be any inverse polynomial in all the other parameters. So the running time of our algorithm and sample complexity will depend on polynomially in 1 over rho. So the algorithm succeeds with high probability over the perturbation and also over the sampling procedure afterwards. Similarly, we can generalize this result by, instead of the zero mean Gaussians, we can learn general Gaussians. They can have arbitrary mean and covariance matrices as long as they are perturbed. Still, the guarantee is very similar.
I guess you can think of rho as interpolating between worst case and completely random case.
Yes, right. Yeah, if rho is really large, then it's like a completely random case. And if rho is zero, it's a worst case. So our algorithm is also based on method of moments. In fact, our algorithm will use third, fourth, and sixth moments. So only constant order of moments. And in this talk, I'm really going to just focus on this first result, the zero mean case. And in some sense, you should not think about this as a very simple special case of the general problem. This is actually one of the harder cases. There are these algorithms that work for learning mixture of Gaussians when the means are separated. But in this case, of course, they are all the same. And also, since we are using method of moments, if the Gaussians all have zero mean, then the third order moment is just all zeros. In general, all the odds moment are all zeros, so we don't get any information from those. So how do we learn a mixture of zero-mean Gaussians? Well, here's the algorithm outline, which shouldn't make sense now, so let's remove these steps. I will go step by step back from the solution and see why do we need all these steps and how do we do all those steps. So what's the main difficulty in this case? And or what is the approach that we are trying to take? Well, we know how to learn a mixture of spherical Gaussians. That's what Sham just talked about. Basically, that algorithm reduces to solve this kind of a system. So if we know something that's the sum of lambda I, vi transpose, so that's a matrix. We know something else that's lambda I, vi tensor vi 3 times. So this was the second and third moment for, not for the Gaussian, but for the topic model. For the Gaussian, you do something else to make them into this form. So we know how to solve this problem to get the lambda i's and vi's if the vi's are linearly independent. So we want to apply the same thing to the mixture of general Gaussians problem. So again, we will think of this lambda i's as the mixing weights. And these vi's, we don't have means anymore. So these vi's, think of them as the vectorized version of the covariance matrix. So if we can get something like that, we will be able to apply the tensor decomposition algorithm. So now, of course, the covariance matrix lives in second order. So this is a product of second order terms. So it should live in the fourth order moment. So let's try, we would hope that the fourth order moment of the tensor look like this. So basically, if you write this guy as a matrix with I1, I2 on one set of coordinates and I3, I4 on the other side, this is really a low-rank matrix that's equal to Wj times the vectorized version of sigma times the vectorized version of sigma transpose. So this guy is very similar to this guy. So if we know this, and we know the same thing for the sixth order moment, then we will be done. We can directly apply this algorithm. But then the problem is this true? Is this equation true? But if you look at the equation for a while, you will realize that this cannot be true. This is really just wishful thinking because the left-hand side is really symmetric, right? I can permute I1, I2, I3, I4, no matter how I permute, it's the same number. This right-hand side is not as symmetric. If I say swap I2 and I3, I will get a different number. So these two cannot be the same. So in fact, we can, of course, compute the expectation of this fourth order moment for Gaussians. This is known as Easterly's theorem. By Easterly's theorem, we can compute it, and it looks like this. So it's really a symmetrized version for this. I have all the different choices for breaking these four indices into two sets. So instead of just this one number, we now have two extra terms, and it's not the same as that one. So later in the talk, I will call these guys the unfolded moments. And this guy, M4, will be called the folded moments because it has more symmetry. If we have the unfolded moments, the first order unfolded moments and the sixth order unfolded moments, then we can just apply this tensor decomposition algorithm directly, and we will be done. But unfortunately, what we observe are only these folded moments. So we need some way to get these unfolded moments only by observing the folded moments. And by the way, throughout the talk, all the red letters, all the red things will be unknowns, and all the blue things will be things that we already know. So the problem becomes how do we get unfolded moments? Because once we get them, we can do tensor decomposition and we get the solution we want. So there's a very natural idea to how to get unfolded moments. Also, it doesn't work. It illustrates our ideas. So I'm going to explain it here. So this unfolded, this unfolded moment x4, if you compute it, has roughly n to the 4 over 8 different entries. These we can treat them as unknowns. By observing this folded moment M4, it gives you roughly n to the 4 over 24 linear equations. So this is really n plus 3 equals 4, but it's roughly that. So obviously we don't have enough number of equations. So we need some more structure on this unfolded moment x4. But what structure do we have? The most natural structure we have is that x4 is a low-rank matrix. It's the sum of k rank 1 components. The rank 1 components are just covariance matrix times the transpose. So then the problem we want to solve looks like we have an unknown low-rank matrix. We get all these linear equations or linear observations on this low-rank matrix. Then we want to recover this low-rank matrix. So this is called the matrix sensing problem. It's a well-studied problem. And there are many nice results. For example, this result of Ben Recht and Fazel and Pablo here. They show that when the linear equations satisfy the matrix RIP property, then we can uniquely determine this low-rank matrix X4 given this observation M4. Then the problem becomes, does our linear observation satisfy this matrix RIP property? Unfortunately, the answer is no. This is not satisfied in our case. We show there exist two mixtures of Gaussians with very different unfolded moments, but they give the same M4. So this property cannot hold. There are many other properties in the literature, but none of them works in this smooth analysis setting. If they don't work for some particular point, even if you perturb them, you cannot hope the properties to be suddenly satisfied. So we need to use some other ways to get the unfolded moments. Well, the idea is still, because it's a low-rank matrix, we can use this low-rank property to reduce the number of variables. Basically, if we know the span of the covariance matrices, so this should really think about the span of the vectorization of this covariance matrix. It's in n plus 1 choose 2 dimensional space. And U itself has dimension k. So if we have a matrix that's n plus 1 choose 2 by k, that is the span of all these covariance matrices, then we can really write this X4 matrix as U times some Y4 times U transpose, where Y4 is now only a k by k matrix. And if we know U, then this is a known linear transformation between Y4 and X4.
When you take the span, you've taken some canonical vectorization of the covariance matrix?
Yeah, yes, you take a canonical vectorization. You can have any vectorization you like. So we know that M4 gives n to the 4 over 24 linear equations on these variables X4. All these can be translated into linear equations on Y4 because Y4 and X4 are linearly related. So we still have n to the 4 over 24 equations. But now Y4, how many variables does it have? It only has like k squared over 2 variables. So the number of equations is now much larger than the number of variables. So we can hope that once we solve this linear system, it will give us a unique solution because we have many more equations than the number of variables. But of course, this is not in general true. We need to show that the coefficient of this linear system should be a matrix that is not just full rank, but robustly full rank, in the sense that it has large smallest singular value. Therefore, when we do the inverse, it's a very stable operation. We can indeed show that, and the proof depends heavily on the perturbation that we have in the smooth analysis setting. Without the perturbation, this is not even true. So in this way, we can get the matrix X4. And similarly, we can also reduce the number of variables in X6 using the same idea, and we can find X6 using a system of linear equations. So now the problem becomes, how do we find the span of the covariance matrices? Once we know that, we know how to proceed.
Is there any connection to Foucault?
Yeah, so it does not directly connect to Foucault. It's also using the structure of the moments, but in a different way. It's very specialized to the mixture of Gaussian setting. Yeah, so how do we find the span of the covariance matrices? So the idea we have is maybe we can look at the slices of these moments. So let's look at a two-dimensional slice of the fourth moment tensor M4. So here I'm using some MATLAB notation. So this just means ij's submatrix of this fourth order tensor M4. So these two entries are left undetermined. So this submatrix is a two-dimensional slice. You can compute again by using Easterly's theorem. Now please just believe me that if you compute it, it will look like that. And now let's take a closer look. So what is this matrix? This matrix, the first term is actually very nice, right? It's a number. It's the sigma ij, that's a number, times this sigma matrix. So if there are no other terms, only this term, then this matrix will be in the span of the covariance matrices. And that is what we want. But unfortunately, we also have these other terms. But these other terms, they are simple, right? They are a column vector times a row vector, so that's rank 1. Even if you take the sum of k of them, they are still low rank. So basically, if we look at a two-dimensional slice of the fourth moment tensor, what we get is a matrix that's almost in the span we want, except for these lower rank terms. So how do we get rid of these low rank terms? So a simple way is to just try to project to some orthogonal subspace that make all of them disappear. So this S is not very easy to see. Let me draw a picture. So this S, really we have these k different covariance matrices, sigma 1, sigma 2, to sigma k. What this S is trying to do is we fix a set of coordinates h. We take all the columns in h in each of these matrices. This will give us k times h vectors. The span S will be the subspace S will be the span of all these k times h vectors. So if we know this span S, so this will be called S. If we know the span S and somehow the I and J we chose, the I and J here are all in this subset S, in this subset H, then when we project to the orthogonal subspace of S, so this guy will be, of course, in S because it's I's column. This guy is the J's column, and by definition, it should also be in the span S. So when we project to the orthogonal subspace, all these terms should disappear. And what we really have is just the projection of the first term. So basically, we can just take this projection So basically, the S is the span of columns of covariance matrices, and we will choose the set H to have size root n. So the rank or dimension or whatever of S is k times root n, which by our assumption, this is much smaller than n. So in particular, we can hope this to be a space of dimension k times root n instead of span the entire subspace, right? So once we do this projection for any ij that's in this set H, we will get one matrix that has none of these terms, and it's really in the span of the covariance matrices, but after the projection. How many such matrices can we get? We can get, for any ij, we can get one matrix. Ij has to be in H, so we have n choices. But the dimension of the span of the covariance matrices is only k. So we have n vectors in a k-dimensional space. So in the good case, we can hope all these n or n matrices. All these n matrices span the entire k-dimensional space. And again, we need to use smooth analysis to say that this is indeed true. So basically, once we take this slices and take this projection for different ij, we get the span of the covariance matrices in this particular subspace S perp. Okay, so basically we know how to go from here to here. There are two problems left. We need to know how to get the span of the columns in the covariance matrices, the space S. We also need to go from this projection of the span of the covariance matrix to the span of the covariance matrix. Let's focus on the first problem first. So the problem now is how do we find the span of columns of covariance matrices? And the idea is very similar. So recall S is the span, it's really the span of all these columns. We again look at the moment structure, but here instead we look at one-dimensional slices. Again, please believe me that if you do the calculations, this is what you get. And the key observation here is this is the I3's column, this is I2's column, this is I1's column. If all these indices I1, I2, I3 are in this set H, this whole vector must be a vector in the subspace S that we wanted. Now we will just choose all the possible choices for I1, I2, I3. And the number of possible choices is roughly n to the 1.5 because we assume the size of H is square root n. So we have n to the 1.5 vectors, but the dimension of S is k times root n. It's even smaller than n. It's definitely much smaller than n to the 1.5. So again, we can hope all these n to the 1.5 vectors to span the entire subspace S. And in order to show that, we need to show that these coefficients are not degenerate. But what are these coefficients? Well, these coefficients are just entries in the covariance matrix, which by assumption they are randomly perturbed. So it's very likely that the coefficients are not degenerate. And the proof again depends heavily on this smooth analysis setting. So that's how we get the span S. So finally, there's only one step left. So we know how to get the span of covariance matrices, but in some subspace. We really want the span of the entire covariance matrix. So how do we recover the span of the covariance matrix from its projections? Okay, if I have just one projection, this seems very hard, right? I have a projection, the information is lost. I have no way to do that. But I can repeat the previous procedure on two different subsets, say H1 and maybe H2. And if I do this on two different subsets of columns, I will get the projection into two different subspaces. It turns out that S1 and S2, they will be two subspaces that are disjoint. There are no vectors that are in both of the subspace, except, of course, the trivial zero vector. So we repeat on two sets, and basically what we get, it's not exactly that, but you can think of it this way. So we want the span of this whole covariance matrix. In the first projection, maybe we don't see all these entries. In the second projection, we don't see these entries. But we still want to merge these two projections to form the entire matrix. Well, of course, if it's just one matrix, this is very simple, right? I can just use these coordinates and merge them, and I get this matrix. It's slightly harder because I have a linear span of the matrices. A linear subspace of matrices can be represented using many different bases, and they are equivalent only up to a linear transformation. So it's perfectly possible that the linear transformation that I used in this span is different from the linear transformation that I used in this part, in this projection. But notice that I still have many of the common entries. So I can hope to align these two linear bases by aligning them in these common coordinates. Once they agree in the common coordinates, I can just directly read all these entries and get this merged space. So all this is really just basic linear algebra. So here's the algorithm, at least at the end. So basically, we know using moment structures, we can first find the span of columns over there. And if we project to the orthogonal subspace of that, we can use the 2D slices to get the span of the covariance matrices in this subspace. We get this for two different subspaces, and then we merge the result to get the span of the covariance matrix. Now we have the span of the covariance matrix. We can reduce the number of variables and solve systems of linear equations to get the unfolded moments. And now once we have the unfolded moments, we can apply the tensor decomposition algorithm as in the previous talk to get the solution. So in the rest, maybe 5 minutes that I have, let me show you just a very simple lemma in the paper that gives you a flavor of what we need to show for the smooth analysis setting to work. So recall we have this definition of S. We want to say, for example, this S should have rank or dimension exactly k times h. This is quite important in our algorithm. And we want this to happen robustly, that it's not just have rank k times h, but if I collect all these columns and form a matrix, it should be it should have large, smallest singular value. So that is very important in proving the sample complexity bounds. So how do we prove that? Well, we collect all these columns to form this matrix. But by the smooth analysis framework, this is equal to some original worst-case instance plus a perturbation. All these matrices, they have some structure as they are these columns from the covariance matrices. So they have some symmetric structure. So basically, this part is the same as this part, right? This is true for both the original, the true parameters, and the perturbation. We don't want this kind of correlations in the perturbation because we want it to be as random as possible. So we will do it is we just simply ignore all these entries that have correlations. Now we have less number of rows. Since we looked at a submatrix, we know the smallest singular value here can only decrease. So as long as I can show the smallest singular value here is good, I'm okay. Then I want to get rid of this original because it's worst case I have no control over. To do that, I just project to the orthogonal subspace of the column span. Again, because I just looked at projection, the smallest singular value can only decrease. So as long as I can show this guy is good, I'm okay. But after this projection, the original disappears. So the projection is really equal to the projection of a random matrix. But this guy is a random Gaussian matrix. The projection of a random Gaussian matrix is another random Gaussian matrix. So this is a random rectangular Gaussian matrix, and whose singular values we understand very well. And for example, Rudolphson and Shining gives a very nice result that gives very tight bounds on the singular values of rectangular matrices, and we can just use that. And that's just tries to give you a flavor of the proofs that we need to do in this smooth analysis framework. So in conclusion, we show that learning mixture of Gaussians is easy in high dimensions when number of dimensions is much larger than k squared. Even lower order moments, up to 6, can provide lots of information, and we can actually hope to utilize this information by carefully looking at the structure of the moment matrix, moment tensors. There are many open problems, so the most interesting one is, can we relax this? We need the dimension to be larger than 100k squared. Can we probably use some higher moments to reduce this maybe to k or k to the epsilon? Also, our algorithm only works in the smooth analysis setting. It would be nice to have an explicit condition for the covariance matrices. Like in the previous case, we can say if the means are linearly independent, the algorithm works. Here, we don't know how to say anything like that. And finally, this is a new way of decomposing this tensor that's formed by the PSD covariance matrices. Maybe it has some other applications. Thanks.
Any questions for Rong?
Yes, in the projection case, you have many projections. Are you using all of them, or just you take the right number and you think that this is it?
Sorry, well, can you...
Okay, so you started with a subspace, and then you say, I know the projection on a smaller subspace, right?
Yes.
And then you want to reconstruct the subspace, right?
Yes.
So then you have a lot of projections, because which I1, I2,
yes.
Are you using all of them for reconstruction, or only part which sort of the right number, and you hope that this is the right number?
Yes, so in our case, we are lucky because our projections, they are like, they have more than half of the dimensions. So we can just take 2 of them, and that's good enough for us.
You just take 2 at random, and that's 2 at random, let's say 2 random, and merge it, and that's enough. Yes. And you hope that you don't contradict the other projections, right?
Yes, yes.
So are these the high probability statements? Are they? Is the failure probability like inverse polynomial?
No, the failure probability is e to the n to the epsilon, e to the minus n to the epsilon, of course, for some constant epsilon.
Are there any lower bounds on n?
Yes. No, there's no lower bound. There's a lower bound on k and n, because if the k is too small, then all these block things, maybe you don't have enough of them. I didn't state that because when k is small, you can use Moicha and Valence algorithm, and that algorithm, when k is a constant, runs in polynomial time.
But n is a function of k, doesn't it?
N has to be at least 100k squared.
No. That's for the algorithm.
Yes.
Currently.
Oh, you mean the lower bound for the problem? No, we don't know any lower bound for the problem. And I would conjecture that n could be as small as k to the epsilon at least, using as well. But yeah.
Yeah. In the beginning with your crab problem, so you were saying that if you only do one measurement, then you need an exponential number of crabs.
Yes. in the worst case.
In the worst case. So that's, you say it's a worst case, but not sort of in a generic case?
In the generic case, I don't know, but this Moitra and Valent paper, they give this counterexample, this lower bound example that says there are two mixtures of Gaussians that have very different parameters, but they are very close in distribution. So in particular, you cannot hope to distinguish them unless you have exponential in k number of samples. And that is what I mean when I said that.
Intuitively, what's the condition of the covariance matrix? What is it trying to say?
Yeah, it's a lot of things. For example, all these columns, they should be non-degenerate. And covariance matrices themselves should also be non-degenerate. It's just different sub-matrices of that should be non-degenerate.
I see. I mean, is it similar to any other kinds of conditions you people consider?
I don't, not that I know of. And also because these conditions, I can choose a random subset. And so if this subset doesn't work, maybe I can choose a different subset. So I don't know what is the strongest, like the weakest condition we can work with.
Other questions? All right. Let's thank Rong again.